You send a WhatsApp message, then nothing happens. But when the reply comes, it appears instantly. So, how does the system wait without constantly checking?
If you think about it, most of the time nothing is actually happening. No data is being sent, no response is coming back. The connection is just open, waiting. Now imagine this at scale. Not one connection, not 10, not even 100, but thousands, all sitting there doing nothing. So if a server had to constantly check every single one, it would waste a huge amount of CPU time, checking again and again and again, even when nothing is happening. Clearly, that doesn't make sense. So instead of asking, is this connection ready? Modern systems do something much smarter. They flip the question. Tell me only when something becomes ready. This is where the operating system comes in. Instead of letting the application check everything, it hands that responsibility to the kernel because kernel is already managing all the network activity. It already knows when data arrives. So instead of repeatedly asking the same questions, the thread doesn't keep running. It yields control back to the operating system and simply waits to be notified. This idea is called IO multiplexing. epoll is one way to implement it in the Linux kernel. Other systems use different mechanisms, but the idea remains the same. Don't check everything, only react when something becomes ready. Here's what actually happens. First, the application registers all its connections with the kernel. Now, the kernel is watching them. Then, the application stops doing unnecessary work and simply waits. No scanning, no looping, no wasted effort. And when something actually happens, the kernel wakes it up. Not with all connections, but only the ones that are ready. Nothing extra, nothing wasted. Think of it like this. The naive approach is like knocking on every door, asking, is something ready? Again and again. But this model, you don't knock, you wait. And only the doors that have something ready signals you. So you go directly to them and nothing wasted. So the system changes its behavior. It stops asking questions and starts waiting for signals. That single shift removes a huge amount of unnecessary work. This is what enables the event loop model. The event loop follows a very simple pattern. Wait for events. Processes what is ready. Then go back to waiting. Again and again. This is exactly how systems like Node.js and Nginx work. They rely on this model to handle massive numbers of connections efficiently. So in reality, the server is doing very little most of the time. It waits and only moves when something is ready. This is completely a different way of thinking. Not keep doing work, but do work only when needed. In real systems, most connections are idle most of the time. Only a small number are active at any given moment. So instead of wasting effort checking everything, the system focuses only on what matters, and that is what makes it scalable. But this creates a new problem. If that one thread gets stuck doing heavy work, everything else has to wait. Even if other events are ready, this is called event loop blocking. And solving this is the next layer. So now the system becomes clear. The kernel watches all connections. IO multiplexing tells us what's ready. The event loop processes it. And the application runs the logic. Each layer has a clear role, and together they create system that scales efficiently. Understanding this shift from constantly checking to reacting only when needed is what makes modern systems scalable. This is how engineers think, not just about code, but about workflows through the system, layer by layer.